This video is about proof by exhaustion. This is where we prove something is true by showing that it is true for each and every case that could possibly be considered. So sometimes this can be quite quick, sometimes it can be quite a long and laborious process, and sometimes if we're smart about it we can actually solve some quite big problems by breaking them down into a smaller number of cases. So we'll start off with a relatively simple quick one. This says to prove that n squared plus n plus 11 is prime for all integers between 1 and 5. So the only cases we actually need to consider here are the integers, the whole numbers that are between 1 and 5. So that's just 2, 3 and 4. I only need to show that this is true for when n is 2, n is 3 and n is 4. So that's what I've done here. I've shown that when n is 2, we get 2 squared plus 2 plus 11, which is 17, which is a prime number. And then similarly, I've shown that when n is 3 and when n is 4, each of those cases gives me a prime number. So therefore, this statement is true for all of those cases between 1 and 5. Next example, we want to prove that if n is less than 6, and n is a natural number, this means it's a natural number. N belongs to the set of natural numbers. Now, natural numbers are positive integers. So here we're looking at positive integers that are less than 6. So we're looking at 1, 2, 3, 4, and 5. And in each of those cases, I need to show that 2 to the power n is greater than n minus 2 cubed. So that's what I've done here. For each of the cases, when n is 1, n is 2, n is 3, n is 4, and n is 5, I've calculated 2 to the power n, and then I've calculated n minus 2 cubed, and in each of those cases, I've shown that 2 to the power n is greater than n minus 2 cubed. So that is my proof by exhaustion for this question. In each and every case to be considered, I have proved that it is true. Next, prove that n cubed minus 2 is not divisible by 4 for n being a natural number, so again, a positive integer. Now, in this case here, notice that there isn't a limit to the number of n's that I can pick, that I have to prove it for. In this proof, I only had to prove it for 1, 2, 3, 4, and 5. And in this case, I only had to prove it for 2, 3, and 4. So how am I going to break this up so that I can prove this by exhaustion? Prove it for every single case possible? Well, I know that I can split all integers up into them being odd numbers or even numbers. And I can represent even numbers as being 2 times a number, and I can represent odd numbers as being 2 times a number plus 1, or 2 times a number minus 1. It's up to you which way around you do it, really. So, if I can prove that this statement is true for all even numbers, and then if I can prove that this statement is true for all odd numbers, then I will have proved this for each and every possible case, because all numbers are either even or odd. So that's going to be my strategy here. So if n is even, I can say that n is equal to 2 times k. So then, n cubed minus 2 would be equal to 2k cubed minus 2, which is equal to 8k cubed minus 2. Now, I know 8k cubed is divisible by 4 because the 8 is divisible by 4. But when I subtract 2 from a number that is divisible by 4, that means my result will not be divisible by 4. So I can say that 8k cubed is divisible by 4. So 8k cubed minus 2 is not divisible by 4. So that's me proving that if n is an even number, this statement is true. It's not divisible by 4. What about if n is an odd number? Then I could say that n equals 2k plus 1. In which case, my n cubed minus 2 would be equal to 2k plus 1 cubed minus 2. Now, to expand this out, let me just expand the 2k plus 1 cubed. I'm going to do this the long way. You could do this with a binomial theorem if you wanted to, or some of you might know the results off the top of your head. But just to show you where I'm getting mine from, I'm going to do this the old-fashioned way. So expanding those triple brackets. Gives me that. And not forgetting the minus 2. Right. Now I can simplify that a little bit, because I can do the plus 1 and the minus 2 there. Right, now this result, is this going to be divisible by 4 or not? Well, one thing that I notice about this is that this 8k cubed plus 12k squared plus 6k, I notice that that's even because it's got a factor of 2. Therefore, when I take away 1 from that, this is going to be odd. And if this is an odd number, then clearly it can't be divisible by 4. So, 2 times 4k cubed plus 6k squared plus 3k minus 1 is odd. Therefore, is not divisible by 4. So I have shown that if n is an even, then n cubed minus 2 is not divisible by 4. And I have shown that if n is odd, then n cubed minus 2 is not divisible by 4. Therefore, n cubed minus 2 is not divisible by 4 for any positive integer, because all positive integers are either even or odd. So this was a trick of taking all positive integers and splitting them up into odd and even, and then doing proof by exhaustion, proving that it is true in both of those cases, to show that the result is always going to be true. Now, I decided to split, in that case, up into odd and even, into 2 different cases. You could, if you wish, split it into 3 cases. Now, there might be some questions where you're trying to prove 3 different results. And so, rather than splitting it into odd and even, you might decide to split it up into multiples of 3, 1 more than a multiple of 3, or 2 more than a multiple of 3. All numbers can be written as either a multiple of 3, 1 more than a multiple of 3, or 2 more than a multiple of 3. So there isn't just one particular way that you can split integers up. There's lots of different ways you can do it, and depending on the question, you will need to decide which is the best way to do it.